All right, let's jump right into this explainer and uncover the absolutely high-octane physics of how X-rays are forged and the literal atomic battles they wage inside the human body. We're drawing on some fascinating material from the BMRIT Radiotalk series out of AIIMS Bibinagar today. And alongside our virtual lab team, Priya, Arjun, and Mira, we're going to explore the fundamental scientific mechanisms that make modern diagnostic imaging possible. Honestly, this isn't just some dry textbook look at physics. We are talking about a dramatic, invisible story of pure energy, extreme acceleration, and microscopic collisions that all go down in a fraction of a second. You know, what's really wild about this whole field is how the origin story starts with just a pure accidental observation. Picture this. It's a Friday night, November 8, 1895. Wilhelm Conrad Röntgen is working late in his lab in Würzburg, messing around with cathode ray tubes. Suddenly, out of nowhere, he notices something super weird. A fluorescent screen all the way across the room just starts glowing. Now, cathode rays couldn't possibly travel that far through the air, so he realizes some invisible, completely unknown force is lighting it up. Just days later, he captures the very first medical X-ray of his wife's hand, and by 1901, boom, he wins the first ever Nobel Prize in physics. I love this quote because it perfectly captures the sheer awe of that moment. He literally called it X-ray, using X as the mathematical symbol for the unknown. He didn't even fully understand the electromagnetic waves he was wielding, yet he completely revolutionized medicine overnight. He just systematically observed what this invisible force could do, documented it, and practically gave us superpowers, the ability to peer inside a living human body without ever picking up a scalpel. Part 1. Firing the electron cannon. Okay, let's transition from the history books into the crazy engineering of how we intentionally generate these waves today. So, to actually harness this power, we have to ask a pretty big question. How exactly do we deliberately create the unknown? How do you transform fast-moving projectiles into penetrating energy? Well, the secret is in manipulating fundamental atomic particles and putting them through some seriously extreme physical forces. Our virtual lab tech, Mira, always says this energy is literally born in fire. And she's right. Step 1, we crank a current through a tiny tungsten filament until it gets so incredibly hot that it actually boils off electrons. This is called thermionic emission. Then, in step 2, we apply a massive high voltage, we call that kVp, to accelerate those little electrons across a vacuum at mind-blowing speeds. Finally, step 3, they violently smash into the heavy, positively charged tungsten target anode. It's this sudden, brutal braking action that converts their kinetic energy into X-ray photons. It's basically like crashing a microscopic sports car into a titanium wall at light speed. Part 2. Braking and characteristic rays. Now let's see what happens during that microscopic crash. When those accelerated electrons slam into the tungsten, two completely distinct types of energy waves are forged. It's not just one uniform beam. Arjun is always fascinated by this dual attack. First, you have Bremsstrahlung, which literally translates from German to braking radiation. This is a broad, continuous blast of energy that happens when an incoming electron has a near miss with the nucleus of a tungsten atom. The nucleus pulls on it, slams on the brakes, and that lost kinetic energy turns into an X-ray photon. But then you have characteristic radiation, which is like a precision sniper strike. This happens when the incoming electron physically crashes right into an inner K-shell electron, knocking it completely out of orbit. When a higher-up electron drops down to fill that newly empty space, it releases a very specific fixed energy photon. Two unique mechanisms operating side by side. But here's the catch. There is a magic threshold at play, and that number is 70. You absolutely need at least 70 kVp to knock out a tungsten K-shell electron. Why? Because the binding energy holding those inner electrons tight is right around 69.5 keV. So if your machine is set below 70, your electron projectiles just kind of bounce off without ejecting anything, and your entire beam will be 100% Bremsstrahlung braking radiation. It is completely an all-or-nothing requirement. Think of this as our ultimate control panel. We can totally manipulate our energy arsenal. Need more penetrating power? You bump up the kVp, which shifts the maximum photon energy up. Need a higher shear volume of radiation? You increase the MAS, which just gives you more of everything, a higher quantity of photons. The target material's atomic number, or Z, actually dictates where those characteristic peaks happen. And finally, filtration. By putting roughly 2.5 millimeters of aluminum equivalent right in the beam's path, we filter out all the weak, low-energy photons. Those weak ones wouldn't even make it through the patient to the image receptor anyway, so filtering them out significantly drops the radiation dose to the patient. It's a total win-win. Part 3. The battle. Interaction with matter. Let's leave the machine now and enter the complex landscape of human biology. So our newly forged X-ray beam finally strikes the patient, and the very first interaction we need to talk about is the photoelectric effect. In this scenario, the incoming X-ray photon hits an atom inside the patient and transfers absolutely all of its energy to an inner shell electron, ejecting it. The photon ceases to exist entirely. It totally sacrifices itself. There's no scatter, no ricochet, just complete absorption. And this is exactly why bones look beautifully bright and clear on an X-ray image. The photon gave its life to create that stark white contrast. Now, Priya always points out the math behind this magic, and it's super cool. The photoelectric effect is proportional to the atomic number cubed, Z cubed. That means even tiny increases in an element's atomic number result in massive exponential spikes in X-ray absorption. Soft tissue has a pretty low atomic number, so X-rays just pass right on through. But hit the calcium in a bone, which has an atomic number of 20, or injected iodine at 53, and the beam is fiercely absorbed. They become absolute shields against lower energy beams, painting that vivid contrast we rely on. But hey, the body fights back. Enter Compton scatter. Instead of a clean absorption, the incoming photon bounces off an outer shell electron, ejects it, and then deflects like a rogue projectile. The photon actually survives this encounter, but it loses some energy and changes direction, just pinging off through the tissue in completely unpredictable, chaotic ways. And honestly, this makes Compton scatter our greatest enemy in diagnostic imaging. Above 30 keV in soft tissue, this rogue scattering just takes over. Because these scattered photons are hitting the image receptor from completely wrong angles, they carry zero useful anatomical information. They just lay down this ugly haze of fog that completely destroys our pristine contrast. Worse yet, this scattered radiation is exactly what bounces out of the patient and hits the technologist standing nearby, making it the absolute #1 occupational hazard in our field. Right, finally, let's talk about the ultimate high-level technique, pair production. Now, this doesn't happen in your standard chest X-ray. You need extreme energy for this, specifically greater than 1.02 MeV. When a photon that incredibly powerful approaches an atomic nucleus, it literally vanishes and spontaneously transforms into mass. It creates an electron and an antimatter positron. Yes, antimatter. That positron then instantly collides with a nearby electron, annihilating them both and firing off 2 gamma photons in perfectly opposite directions. It's quite literally pure Einsteinian physics happening right inside a PET scanner. So if we look at our master strategy screen here, you can see the whole clinical domain mapped out. Diagnostic imaging is basically this constant, intense tug of war. We are always trying to foster the complete absorption of the photoelectric effect to get that beautiful, crisp contrast, while simultaneously trying to mitigate the noisy, image-ruining ricochets of Compton scatter. And then off to the side, you have pair production reigning supreme in the high-energy world of PET scanning. Part 4. The final radiographic image. Let's bring this all together and look at the actual result. At the end of the day, every medical image you look at is simply a map of the survivors of these atomic clashes. You aren't looking at the whole beam, you're looking at the aftermath. This concept is called differential attenuation. The diagnostic shadows we read, the bright bones, the dark air-filled lungs, the vessels, they're all carved out by that differential pattern of absorption, scatter, and transmission. Photons hit bone, get absorbed photoelectrically, and leave a bright white spot. Photons that pass through the air in the lungs hit the receptor directly and turn it dark. It's this precise, varied pattern of survivors making it through the perilous journey of the human body that gives us our final anatomical picture. So knowing that every single scan represents literally millions of subatomic collisions, you gotta wonder, what hidden secrets of your own physiology are just waiting to be illuminated by the unknown? From that accidental Friday night discovery back in 1895 to the incredible violent atomic interactions happening in modern hospitals every single second, the science of X-rays is just nothing short of miraculous. Thank you so much for joining me, Priya, Arjun, and Meera on this explainer today. I really hope you leave with a newly energized perspective on the invisible forces at work the very next time you see a medical image.